Okay, good morning. This is Professor David J. De Los Reyes. Okay, it's September 23, 2023. The time is 6:31 a.m. Okay, my topic for this session will be long video format discussion on what they call this AC machines, and this will now be lesson number 19. Okay, let's proceed. The new topic for this morning will be alternating current machines, lesson number 19, and the title of the topic is Example Problem on Eddy Current Loss. Eddy current loss is one of the component of the losses of the transformer. That is actually a part of the core loss. Okay, I will try to read the problem. The eddy current loss in a 6660 Hz transformer is 280 watts. What will be the loss, meaning the eddy current loss, if the transformer is reconnected or connected to a new input voltage? The first one is 2300, next one is 2400, and the next one is 2200. So you see the difference. Originally it was connected to 6600, the eddy current loss is 280. So the problem is asking if the applied voltage is 2300, what will be the eddy current loss? And again, if the applied voltage is 2400, what will be the eddy current loss? And lastly, if the applied voltage is 2200, what will be the applied voltage? Okay, let's try to bring out the solution. We bring out first the given. What is given is capital letter P with the subscript E, meaning the eddy current loss is 280 watts. The terminal voltage is 6600 volts. Right? The original terminal voltage supplied is 6600. Okay, it's this. Okay, let's try to bring out the solution. The problem is just asking for the eddy current loss. We are solving for the eddy current loss. Okay, capital letter P with the subscript E will be K2 times the square of the induced voltage. In here, E will be equal to E. E will be equal to B, the given terminal voltage. It is equal to D. Because this is the terminal voltage, the induced voltage on the winding is E, but for simplicity of solution, okay, since there are no other parameters given to compute for E, we will assume that E is equal to the terminal voltage. Whatever the terminal voltage here, we assume that it is equal to the induced voltage. But they are not equal, but they are almost equal, okay? So for simplicity of solution, because no other parameters is given to compute for E, we will assume that the given terminal voltage is equal to E. Okay, so for the first condition, the eddy current loss is 280 when the terminal voltage applied is 6600. Okay, so to compute for the eddy current loss when the voltage is 2300, 2400, and 2200, we must have to compute first for this K2 here, right? So if we try to compute for K2, K2 will be PE, the eddy current loss over the induced voltage quantity square, okay? And this should be 280. And since I said that E is equal to, this is B is equal to E, okay? We can use the given terminal voltage in lieu of the, what you call this, induced voltage. So this should be 6600 quantity square. If you try to square this one, this is a very big number. It is by the million. So we divide that by 280. The ratio will be 6.428. We square this one, it got a power of 1 million, right? It will raise up. So this is 6.428 times 10 to the negative 6. Okay. That is the needed K for the given transformer. Okay, so at any input voltage given, we can use this one here. So using the same formula, PE will be K2 times E squared. Okay, We now know K2, right? So when the applied voltage is 2300, this will now be 2300. Okay, what will be the eddy current loss? So we'll be using this formula. This is the K, and the new applied voltage is 2300 as per given condition A. This is 2300 quantity square. If we try to square this one, this is by the million. Okay, so it will cancel out with this. So what will come out will be 6.428 by a certain small value here. And what comes out for the eddy current loss is 34 watts. Okay, why it's lesser? It's lesser because the given terminal voltage is 2300. Originally, it was 6600. And the voltage actually varies as the square of the voltage. So if you square this one, this is a very big one. But for the second one, even though you square this one, but this is almost 3 times the other. So actually, the eddy current loss will be lesser. It is 34 watts. That is when the applied voltage is 2300. So as you can see, the eddy current loss is not affected by frequency because it on the formula there is no frequency here. Frequency, nada, right? Okay, letter B. When the applied voltage is 2400, this will now be 2400. Right? Frequency 60 Hertz. It doesn't matter what will be the frequency. So again, by using the same formula, 6.428 times 10 to the negative 6, the new applied voltage is 2400 now, so this should be 2400 square. This is 1 over 1 million. If you square this one, this is by the million, it will cancel out. So what will come out will be 6.428 times a certain value here. What will come out will be 37 watts. It's a little bit bigger than the first one because the first one is at 2300 and the next one is at 2400. Okay. Third one. When the applied voltage is 2200 and 25 Hertz, this will now be 2200. Right? So again, by using the same formula, 6.428 times 10 to the negative 6, it is the same formula. The only changing is the applied voltage, 2200 quantity square. Again, this will be by the million, it will cancel out with this. So if we try to multiply the 6.428 times the significant number here, it will be 31.11 watts. It's the smallest one, 31.11 watts. You see, the first one is 2300. The eddy current loss is 34. At 2400, am I still on camera? At 2400, it is 37. Okay, this is bigger, so supposed to be the eddy current loss will be bigger. And at 2200, the last one, this should be the smallest. Okay, what comes out is 31.11 watts. This is watts. So actually, eddy current loss varies inversely with the square of the applied voltage. Okay, varies inversely. Eddy current loss varies inversely as the square of the voltage. Okay, this is independent of the frequency. Okay, that's it, guys. That's the way how to compute the eddy current loss of the transformer with the given applied terminal voltages. Okay, good morning from Los Angeles, Professor David J.